Hello, we're going to talk about magnitude, distance, collinear vectors, and midpoints of vectors in 3D space. So I've done my best here to draw a three-dimensional vector, and if we let V have the components V1, V2, and V3, you can kind of see this is my x distance. So this component right here, I guess I can write it right here. This would be v sub 1. This is my y distance, so this distance from here to here is v sub 2, and then this distance right here is v sub 3, right? So right here. And we're going to try to figure out what the magnitude of v is, right? So first, let's look. The first thing I want you to look at is, let's go ahead and, yeah, let's look at if we have a right triangle right here, right? And this is a right triangle. So if I let this length right here, let's call that c, right? Then I know that c squared is going to be equal to this side right here is v sub 1, because that's the same as here. So c squared is going to be v sub 1 squared plus v sub 2 squared, right? But then we also have another right triangle. If we look right here, right here, this triangle right here, and we can see that the length, the magnitude v, so I could say the length of our actual vector, and that's its length squared, is going to be c squared, right? Which we already know, and we'll be able to plug that in later. But this length here is v sub 3 plus v sub 3 squared. And then since we know from substitution, we know that c squared is equal to v sub 1 squared plus v sub 2 squared, then the magnitude of our vector, three-dimensional vector squared, is going to be v sub 1 squared plus v sub 2 squared plus v sub 3 squared. And then we can go ahead and write the formula for the magnitude of a three-dimensional variable. If we take the square root, it's going to be square root of v sub 1 squared plus v sub 2 squared plus v sub 3 squared, right? So we see that in 3D, it's the same thing as in 2D, just we're going to have an extra component, right? And that's that one, right? And then we can find if we have, let's say we have a vector a b, and we know that a has the point x1, y1, z1, and b has the point x2, y2, z2, then the distance, we know that the distance of segment AB is going to be the magnitude of, well, this is just a segment, if we just think of it as a segment AB, is the magnitude of AB, and that's going to be the square root. Let's see if I can get it all in here. So it's going to be x2 minus x1 squared plus y2 minus y1 squared, all squared, plus z1 minus z2 minus z1 squared. And that gives us the distance, right? And the same thing happens for collinear vectors, right? If we have collinear vectors, then let's say vector u, right, is going to be some scalar lambda times b, and that's going to hold just like it did in 2D and 3D. And the unit vector would be the same thing. If we wanted to make this its unit for v, right, if we let u be the unit vector, if u is the unit vector, meaning a vector of magnitude 1 of this vector in the same direction, right, then u is going to be, you take the vector v and you're going to scale it, divide it by its magnitude right here. And then using, and if, since v1 is equal to v1, v2, v3, then I can go ahead and write this as component v1 over the square root of v1 squared plus v2 squared plus v3 squared, right? The y component v2, the square root v1 squared plus v2 squared plus v3 squared, and then finally the last component, b3, is the square root of b1 squared plus b2 squared plus b3 squared. So these are all the same, right? And we have our parallel vectors right up here for collinear. We have our unit vectors all pretty much the same. Also, the midpoint, if you remember from algebra, is going to end up being the same between two vectors. So the midpoint, if you remember from algebra, you're going to have the average between them plus x2 over 2 and y1 plus y2 over 2, and then z1 plus z2 over 2. And you've probably seen that in a geometry class in the past, or algebra too. So let's go ahead and look at a couple examples. Let's see, example 22, it says vector v1, 2, 3, determine the component form of the unit vector u in the direction of v. So I want to find the unit vector, but first I'm going to find the magnitude of v, right? The magnitude of v is going to be 1 squared plus 2 squared plus 3 squared. So the magnitude of v, right, is going to be square root of, what is this, 9? 9 plus 4 is 9 plus 4 is 13, plus that's 14. So this is going to be, well, let's, magnitude of v is just going to be the square root of 14. Good. So the unit vector u in that direction, right, is going to be, once I scale it 1 over, it's going to be 1 over the square root of 14, 2 over the square root of 14, and then 3 over the square root of 14. Good. That's the unit direction, the unit vector in the direction of v. So this is the unit vector. If you take the magnitude that's going to be this. Now, find the unit vectors parallel to this. Well, that would just be this same vector here. I'm just going to make it plus or minus, right? Because both, whichever direction, they end up being parallel, and it's still a unit vector, so it'd be plus or minus, right? Then the vector with magnitude 7, right, in the direction of v. It has to be in the direction of v, right? So I know I'd have to take some lambda times my unit vector, which is 1 over this vector right down here. Let me see. I'd have lambda times my unit vector, which is 1 over square root of 14, 2 over square root of 14, and 3 over square root of 14. And then if I find its magnitude, it's got to be equal to 7, right? I'm messing up here again. Good, so that's going to be equal to 7, right? Which is going to be the square root of lambda 1 over square root of 14 all squared plus lambda 2 over square root of 14 squared plus lambda 3 over square root of 14, right, squared equals 7. And then when I take the square both sides, and I'm going to end up with, looks like I'm going to end up with lambda 14, right? If I square root of 14, I'm going to get 14. It's going to be lambda squared, though, plus 2 lambda over 14, lambda squared, plus, actually this should be 4, my bad, because 2 squared is 4. Then it's going to be 9 lambda squared over 14 equals, when I square both sides, I'm going to get 49. And then this, I add these up. These are going to add up to 14 over 14. It's going to be lambda squared equals 49. And then lambda could be plus or minus 7. But it asked me for the vector with magnitude 7 in the direction in the direction of v. So I'd have to, I want it in the direction of v, so it's going to be, take that unit vector right here and multiply it by positive 7, make sure I don't go in the opposite direction. So if I'll just call this vector a, it's going to be 7 over square root of 14, 14 over square root 14 and 21 over square root 14. This is the vector that will have magnitude 7 in the direction of vector v that we have there. And then our last one that we have here, that we're going to look over, it's example 23. It says, given the points A, -1, 3, 5, and B, 3, -5, 1, find M such that, when I write that, that means such that AM equals MB, and then what is M in relation to AB? Good. Well, you can kind of see the answer right up here. AM is equal to AMB, so you can kind of see what the answer is, so, and we'll go over that in a sec. But AM, if I were to find AM, right, well, M, I don't know what M is, so I'm going to call that XY, right? Good. So if I find a vector AM, right, that would be X plus 1, right? That would be vector X plus 1, and then, oh, I'm sorry, M should be, my bad, it's a three-dimensional vector, right? So so this would be x, y, z, right? My bad. And then it would be y minus 3, and then it would be z minus 5. Good. And that has to be equal to mb, so that would be x minus 3, y plus 5, and then z minus 1. Good. So I know these have to be equal, and I can set up a solve for x here. So I can say I could solve for each variable. X plus 1 equals x minus 3. So, I made a mistake. Let me see. Yep, MB, I should have started B. These need to be inverted. My bad. So if I did MB, I got to start with B, so it's 3 minus x, right? So 3 minus x, -5 minus y, 1 minus z, right? Now I can go ahead and solve for these now. And then I'm going to have x plus 1 equals 3 minus x. This is going to be 2x minus 2 minus equals 2, so x is equal to 1, so I got that one. Y minus 3 equals -5 minus y, so I'm going to have 2y equals -2, right? So, yep, and then y is equal to -1, and then z is z minus 5. Z minus 5 equals 1 minus z. Then I'm going to have 2z equals 4, right? And then z is equal to 2. So what is m equal to? It's 1, -1, 2. Wait, my bad. This should have been plus 5. This should have been 6. So this should have been 2 divided by 6 is 3. So real quick. So now I know this is 3, and I was able to find my m. And if you didn't notice, the last one, it says what is m in relation to AB? Well, if AM is equal to MB, this guy right here, M, is a midpoint. And there you go. Thanks, guys.